Thanks all for joining. I hope this is going to be an informative talk. We're going to try to keep it short and sweet, but have them as frequently as possible. My plan is that once my video from the Nexus conference comes out, that and you guys have a chance to look at it, that I'll have 3 meetups, maybe every 2 weeks. I don't know yet, depending on what the interest is, and go through each one of those demos hands-on right here, and so you can see what we're trying to do. And then later follow it up about how we're going to package Lisp and Tritium together, and show you some of the things to solicit feedback from you and reactions of how we're packaging it, how we can get miners and wallets and stuff to talk to the daemon with Lisp. So that's kind of the plan going forward. If you have any clarification questions, go ahead and click the raise hand button so I know to stop talking and allow someone to take the floor and talk. And then we're going to have 15 minutes. So I'm going to try to talk for 30 minutes and then leave 15 minutes for questions, discussions. So you can just start queuing up your questions in the chat room if you want. Does that sound good for everyone? I assume my volume's okay. If there's any audio problems, please interrupt. I'm going to now share my screen and bring up the slides. Yeah, go ahead.
That sounds good. Ready? I can hear you.
Okay. Can you guys see the slides okay? Are they being cut off at all or anything?
Yeah, looks good.
Didn't hear that. Somebody said something?
Yeah, it looks good, Dino. It's all good.
Okay, great. And so, so what I'm going to do is I'm going to keep it in this mode so you could see my pointer. So I make references, you can see it. You see me circling the pointer around my name and Colin's name? Just want to make sure that's working. And maybe from you guys that are more than 200 milliseconds away, it's going pretty slow. And let me see if I can see the chat group while I'm, no, let's see. Hold on one second. I can't see the chat while I'm sharing my screen. Let me see. As a presenter, I can't see the chat. So I'll have to move back and forth between screens, I think, while I'm in share mode. Okay, so let's get started. So Colin and I decided to collaborate early when we started working together back in March. We started working together like in January, February timeframe. And then I asked him to come to IETF so I can introduce him to a standards community. IETF stands for Internet Engineering Task Force. And we decided to co-author a draft together to build a decentralized mapping system for Lisp. Now, Lisp already has a distributed and decentralized mapping system, but we want to make it even more so. And this is kind of an advanced topic, but just want to show you what we're thinking about the future for a decentralized internet and how these could run on miner nodes, wallet nodes, daemon nodes, satellite nodes, that sort of thing. I'm going to probably have future meetups where I'm going to talk more about the basics of Lisp, but this will hopefully give you an idea of how the control plane works for Lisp. And if there's any acronyms or anything you don't understand, please stop me and I'll explain it, because I know this is new to a lot of people. And I know a lot of people don't focus on networking and the internet down at the network layer. So, this is for educational purposes, so please ask away. Okay, so these things called XTRs are called tunnel routers. I don't know if the people who went to the conference were able to see that we're going to package Lisp at the network layer with Nexus at the application layer. And so an XTR usually is a router of sorts, but it can be placed in an end node. An end node meaning a host that is running an application like Nexus. So when we talk about XTRs, we're talking about a node that's running the Nexus daemon at least. Could be a miner, could be a wallet, could be just a seed node. So these things are called XTRs. And they're basically on the edge of the overlay. So LISP is an overlay where it basically builds a network on top of the capital I internet. So it can be secure. It can be like a virtual private network. You can decide who comes and goes from this network. And we're going to use that for different types of nodes, different types of test networks, maybe between the L1, L2, and L3 locks for each release of the TAO. So what we want to do is we want the mapping system to not depend on a third party. So arguably the mapping system today does depend on a third party. But what if the XTRs could be multi-homed and roam to inform each other about new RLOCs? And I'll show you this with a picture on the next slide. What if these LISP XTRs could have their own mapping system? So let's build a purely democratized and decentralized control plane. Now, throughout the presentation, we're going to talk about endpoint IDs, which are addresses that are assigned to applications and hosts. And they are only known to the overlay. And the routing locators are what's known to the underlying internet, which we call the underlay. So if two Nexus nodes want to talk to each other, they will make a connection across their EIDs. But the way the packets actually get routed is another header is put on the packet and then gets moved to their routing locators. So these Nexus nodes could have more than one locator, and the LISP running in the Nexus node can decide which locator to send to. In other words, increasing performance, avoiding delays, lowering latency, these sorts of things. So wherever you see green addresses or green, we're referring to endpoint IDs, and wherever you see red, we're referring to routing locators. So EIDs are part of the overlay, and routing locators are part of the underlay. Okay, so today's mapping system works like this, is that the mapping system is actually part of the core infrastructure, just like the domain name system is for resolving names on the internet. And everything in the internet is in this RLOC space, which means the underlying routing system knows how to route across these red addresses. Typically, a LISP site looks like one of these four sites where all the nodes have an EID assigned to it. And then there's these border routers that run LISP called XTRs. Like I said previously, is we're going to make it one and the same. So if we have a bunch of Nexus nodes running here, they're each going to be XTRs so they can handle their own routing from place to place. Okay, this is just showing that the mapping system here is pretty distributed and decentralized, but it's not run by the people that are operating these XTR nodes or the Nexus nodes themselves. Just like the DNS system, you depend on some internet infrastructure to resolve names. Today, when you want to resolve EIDs, you have to depend on infrastructure components. You know, eventually there's going to be companies that are going to own that and have control of it. So it is quite distributed and decentralized because there's going to be many companies that are going to run this particular mapping system, but it's not really run by the nodes. So why do we want the nodes to run them themselves? Well, you know, what if you're in a neighborhood in the suburbs or in a city or something, and you actually lose your connectivity? Those white lines are links into the underlying internet. Now, if you lose those links, you're pretty much cut off from the network. It's like a single point of failure. But you have all this wireless connectivity on the nodes that are making up each of that EID space, and they can actually talk to each other, right? Well, if they can talk to each other directly, but don't know the RLOCs of each other, then they're not going to be able to talk. And if they need to resolve the EIDs to RLOC mappings from a mapping system that's in the internet and you can't reach them, then it's pretty useless. So by distributing the mapping system to all the XTRs, these two sites, maybe those are two different houses in a neighborhood, can actually talk to each other because they have all the mappings to everybody. In fact, they still have the mappings to the guys that are on the other side as well, right? They might be old mappings that when the links were up were cached, but the fact that they have those mappings could be useful if there's any kind of backdoor connectivity. But what we're trying to show here is that, you know, the the internet was partitioned by these folks, but some of them could still be co-located and talk to each other. So the way this works in LISP today is that these XTRs actually register their mappings. So on the right-hand side, we're showing that there's this IPv6 address that's assigned to a Nexus node, perhaps, and it's actually registering to both of the map servers and the mapping system. The mapping system is made up of nodes called map resolvers and map servers. And XTR2, in this case, is sending the register saying that I'm telling you that I'm the RLOC for this /48 address, and I'm telling you map server 2 and you map server 4. And the way we plan on deploying this for Nexus is we may make initially some of the seed nodes map servers, and so we can still use this particular model, okay? So just to let you know is that LISP in general is a very mature technology, and we've been developing it for 10 years, but LISP-Decent is only 6 months old. So that kind of just gives you an idea of where we've been and where we want to go. And so when we start deploying Nexus and LISP with Tritium, we're going to start with this decentralized. We're going to start with a distributed model using the seed nodes, but eventually we're going to migrate to the LISP-Decent way of doing things. So this is the way it works today. So what we want to do is we want to decentralize this map server. What if each XTR on their own could be a map server? And what if each XTR could map register to each XTR? Then the mapping system would be synchronized among all the nodes who want to talk to each other. And they wouldn't even need a map resolver because they can just do a lookup in their own local database to find anybody. And so doing lookups would be very fast because you don't have to now send messages on the network to resolve these mappings. So how do you define a mapping system? Well, a consolidated mapping system is identified by a multicast group address. So if we can say that if there's maybe there's the Upper West Side in New York City that's going to be able to talk to each other, and then there's the Upper East Side. Maybe they're going to run their own mapping system because they don't want to talk to each other. Well, you can then allocate a multicast group address for the ones on the West versus the East, and then they can only talk to each other, allowing privacy and scope control on those systems. The XTRs that are part of the mapping system join this multicast group, and then when they each send map registers, they send it to the group, so all other XTRs will receive it within that scoped area. And so we'll have efficient distribution when the underlay supports multicast, or we'll do a head-end replication by each XTR. So if the Upper East Side is all connected on a Wi-Fi network where multicast is available by the underlay by a set of access points or Wi-Fi mesh, then we only have to send one message and the underlying network sends it to everybody else. So one copy is being transmitted and N copies are being received by all the receivers. If the Upper East Side is going through links that don't support multicast in the underlay, then the head end, in other words, if I'm going to send a register, I then have to replicate it to everybody that's in the system. And we could do this with head end replication mechanisms. So that's just how we try to do it from an efficient point of view. This is kind of a picture on how it would look. Okay, so the Upper West Side are those odd numbered XTRs, 1, 3, and 5. And Upper East Side, let's say, is the 2, 4, and 6. And so what they're doing is they're joining this group 224.222 on the right and 224.111 on the left. I said I was going to be using my pointer and I didn't. So what happens is that all three of these nodes would have these mappings. They would say that 1 is part of the RLOC for 1 is XTR1, the RLOC for 3 is XTR3, the RLOC for 5 is XTR5. So these are the mappings that all three of them would have to each other. So if they lost this internet connectivity here, they could still talk to each other if they had connectivity to each other. And then it's the same thing on the right-hand side. I just used IPv6 addresses. This is using IPv4 addresses. So the idea is that the mapping system now has been relocated in these nodes versus being resident in the capital I internet. Make sense? Okay, I don't know if somebody's talking. Let's see. Okay. So what are the benefits? Well, XTRs only depend on each other. They do so already if they want to talk to each other. So it's not too much of a stretch to say, well, if I want to talk to Anastasia and she's not going to tell me her RLOG, then we're not going to talk very much, right? Like if her and I want to have a conversation, we want to talk on the phone, she has to give me her phone number. If she gave me her phone number once before, then I can call her. So I could have her phone number cached. This is the same thing that we would be doing in these data networks as well. Now, there's no third-party trust or dependencies that exist because we only depend on the things that we talk to, okay? And then a map request lookup has low latency because since each one of these nodes has this exact image, so if XTR5 wants to do a lookup for 3333, which would be part of this prefix, it would just do a local lookup and know that XTR3 is where it needs to encapsulate packets to. Okay. I don't know. Was there a question? Let's see more. No? Okay. I'll keep going. I only have a few more slides and then we can just open up for questions and then I could switch. XTRs build and send one map register for N XTRs. So we kind of solved the push problem. You know, if there's 1,000 of these things that are running, and you have underlying multicast, you send one, and then N XTRs will receive it because the underlying system will replicate it where it needs to do. And this is what we're going to do starting off with L1 locking groups. So Nexus doesn't have to retransmit these messages to N number of peers. So we could scale better, we can scope it, we can have access control to these groups. So multicast is going to help quite a bit. Management is simplified by accessing one XTR. If you want to find the mappings, all you have to do is just ask any one of these and you'll get the same information. That's what synchronized databases allow you to do. Pretty much the same benefits that we saw with peer-to-peer networking. Today in a Nexus peer-to-peer network, you don't have to go ask a peer for a transaction because since you have all transactions stored, you can look it up locally and get the information you need. And since it was verified and put on the blockchain, you know everybody has the same information. So use cases for this.
I'm just thinking to myself.
Go ahead.
Oh, sorry, Dino. I didn't have you on move, but one thing that I was thinking about was with these, with basically the addresses, is there a public domain where they can go back and check them on chain without a key system, or do you have to be granted the key as well in order to check their location details, or I guess their address details?
So these address details are all registered with the mapping system, and those mappings are authenticated as well as using a shared key to allow you to be authorized to talk So for instance, if this guy right here wanted to start registering to the 224.222 group, if it didn't have the shared key among all of them, this registration information would not be cached by the guys on the right-hand side. So this is all done way below the blockchain level and the Nexus level. It's all done at the network layer. Just like all my audio and video packets now are being sent over the IP internet with IP packets, that's what we're talking about here. Okay.
Okay, gotcha. Thanks for clarifying.
No worries. So we think there's more use cases, just cryptocurrency applications. We think emergency networking and mesh networks. We've seen this a lot, like the Katrina hurricane, that people were able to talk to each other because they had these cellular phones. They had phones with interfaces that can talk to each other, and they had IP networks that can address each other, but the applications couldn't work peer-to-peer because there weren't none, and so they couldn't really communicate with each other. So we're seeing a lot of mesh networks and actually cellular networks being built in really remote areas of the world, and we think that these mechanisms are going to be really useful for them. They may be multi-home to Bluetooth, Wi-Fi, and these cellular networks at the same time, but have no internet infrastructure. They should still be able to talk to each other. You know, they have no DNS, they have no certificate authorities to do anything. So how can we do all this stuff on the edges? So this is just the beginning of what we're looking at. Plug and play VPN networking as well. Just like when we use Slack, we're joined to these channels. Those channels are pretty much multicast groups or VPNs that only certain users are allowed to go in there. If you want to break off, if Nelson and I want to break off of Pound General, we direct message to each other. That's the same thing of building these VPNs to go private. We should be able to do these quickly, just like we can at these application layers. And of course, the space networking is really interesting as well, because the low Earth orbit satellites are moving in and out of phase. And so we need to be able to use the ones that we can currently talk to. These are RLOC changes that are happening all the time to nodes that are up there. So we're trying to figure out if we put Nexus nodes directly on the satellites and have them be peer-to-peer relays, or we just make it an underlay for connectivity and we use the LISP overlay on the ground. So we have a lot of different combinations that we can have a future meetup about how we're going to do networking in space. But, you know, the overlay could be on the ground, the underlay could be in space. The overlay could be on terrestrial and in space, and the nodes can be in both places. We could have movement on the ground and movement in space. Count on it, because the Earth rotates. How are we going to make all that work? Do we have a mapping system that's on the ground or also in space? So all these combinations of things we need to address and decide, you know, what's important, what are the right design trade-offs. And of course, shareable economy apps are coming up. Like there's a company called Dove that is allowing us to share each other's bandwidth and CPU on the devices we own. And they want to do that for networking. So maybe, you know, just like Napster was a way for me to download a file from a neighbor, you know, 30 meters away from me, maybe I could use his bandwidth at his house. We've seen Comcast do this in neighborhoods as well. If you ever see Xfinity pop up on your Wi-Fi display, you're actually using a small percentage of somebody's house bandwidth to get access to the internet. So these sorts of things are just going to grow more and more. So, so what we showed at IETF was we had 3 Docker containers running LISP-Decent, and we just wanted to show how it could work. And we decided to not use underlying multicast just to show that head-end replication could work. So the XDRs are doing head-end replication, and we were registering an IPv4 EID prefix and then a name type EID. And all this shows is those are the 3 containers running here, and that 1, 2, and 3 were each of the containers, and they were each registering their own name. So this system N3 was registering 33v3 and Nexus N3, and of course 1 and 2 were registering 111 Nexus N1, and you can see that each one of them had the same information. If you look at how they were registering to this group, and the local nodes knew to replicate to each of the unicast addresses of the XTRs. And this is telling you that packets were moving. So this was a quick screen dump that we showed at the IETF because we had working code. So that's it. I gave you guys 5 extra minutes for questions. I know it was a pretty advanced topic, but we're going to have more that are much simpler in nature. I've heard people say they just want to know, you know, what's networking or Internet 101. So we may have to start there and talk about how the internet just naturally works, and then show you why overlays are important and why Nexus wants to use overlays. And that'll go in a more chronological or, you know, an order that's understandable. But this was just something that we wanted to show you, that how Colin and I are collaborating in the IETF to do something that's pretty advanced. This 00 means was the first version of draft. We already had an update called 01, but we're planning on updating this draft for the fall IETF to show a pull-based way of doing it. So this was pushing mappings to all the Nexus nodes. What we want to do is to be able to find out that certain EIDs are registered to certain places, so we don't have to push them. And so we do a modulus math sort of thing to find out where they're being registered, and therefore we request them in the same place. So we're going to have this is a push mechanism. We're going to have a push and pull part of the document to show that there's 2 ways of doing it. And then Colin is going to do an internet draft on how to DOS attack protect this decent decentralized mapping system by requiring hackers or bad actors to do proof of work. If they really want to disrupt or corrupt the mapping system, they have to work hard at it. And to work hard at it, we're going to force them to do proof of work algorithms, and that slows them down. So this is kind of a novel idea that the cryptocurrency market is bringing down to the lower layers. And so Colin is going to describe that in a spec. And we've been talking about it for a few months now. And so we're going to give it a try and do some prototyping. Again, these are future things, but these are really good ideas just to keep us really ahead of the game. Okay, I'm just going to stop sharing so I can get my other display to see. Oh, tons of questions. Good. Anybody have any questions they want to verbalize before I go through this list? "21 participants, that's great. Okay. Okay, good. LISP stands for Locator ID Separation Protocol. What we're doing is we're changing the semantics of an IP address because today it means both location and identity for a node that's on the internet. And that's a semantic overload. If I want to talk to Anastasia, I know I want to talk to the ID Anastasia, but right now she's in Europe. If she changes location, her IP address changes, but she hasn't changed, right? So what we're doing is we're going to have an EID that's called Anastasia, and then we're going to have routing locators that say Phoenix or Prague or London, and that's basically what we're doing. What I tell people is what local number portability was to the cell phone network is what LISP is going to be to the internet. We all have cell phones, and we could switch providers, we could move around, and those cell phones never change. And it's the underlying network that knows where that phone is at any given time. We don't have this concept and this architecture in the internet right now, and that's what LISP is trying to help do, okay? Hopefully that was clear. Thanks, Paul, for helping out. Is there a way to get someone TR1 from any other way than personally sharing, recorded on chain or database? Oh, that was Nelson's question. I hopefully I answered that. Okay, the one question I have some.
Yeah, you did.
Okay. Okay, Belgian boy, I have some Nexus. I know many of the holders lose some faith. I know that LISP is awesome for Nexus. Why did you choose the Nexus besides other projects out there? Two reasons. Well, three reasons. It's a small project, its market cap is low, and the people are fun to be with. Is that a good answer? The market cap being low is a feature, not a bug, in my opinion. So we can be innovative and make change quickly. Look how hard it is to change the Bitcoin and Ethereum network. You can't change it. You can't get it all right in one shot. This technology has to evolve over time. And if it's architected where it can evolve easily and transition from the old nodes to the new nodes, then this is going to make it successful. So these are the sorts of things that we have to do. And you know, I've told Colin many times we have to figure out ways of upgrading Nexus nodes when we decide to change an architectural constant. And we're hoping that by using registers and creating these global registers that have state about the network, that these nodes can automatically upgrade themselves and still be compatible. That's what we want to do. That's our vision for the future. Can and will an EID be a signature chain in the Nexus implementation? Question from Paul. So these EIDs, especially IPv6 EIDs, can be crypto EIDs. And what that means is some of the bits in that EID are hashes of public keys. Colin has plans on using the crypto EID as part as to be included in the Genesis transaction. So there's tighter coupling between who is sending packets to you and who's signing transactions and blocks. We want to make sure there's not spoofers happening. So we're going to have this tight relationship between the application layer and the network layer. And so Collins code or the blockchain is going to help me be able to put records on the blockchain so people know that these addresses have been allocated, and I'm going to give him security at the network layer to give him more security from the overall holistic system. So that's how we're going to be able to work with each other. Are there any disadvantages to running Lisp? Well, you have to put an extra header on the packet, and some people believe that that's overhead. That's not worth it. Now, the level of indirection requires that extra packet because you don't want the nodes in the network to know about EIDs, especially if we want to create a new version of IP, or the core internet doesn't support IPv6 everywhere. We're going to find that we're going to be using crypto EIDs, which are IPv6 EIDs, but they're going to run over the existing infrastructure. And we want them to reach anybody, anywhere on the internet, which is most likely going to be with IPv4 RLOCs. And we have to make it work through NAT boxes, NAT devices that we all have at home. Any cellular network uses NAT boxes in the mobile carrier's network. All your access points are NAT devices. Your home routers are NAT devices. We just have to make this all work. This has been hard for existing Nexus to make work with using UPnP. So this is another improvement that's going to help. But to get all these benefits, you have to put more bytes on the header, okay? People would argue also that Lisp has added complexity because you're adding another level of indirection. We believe the level of indirection is going to give you many benefits, but everybody does a cost-benefit analysis on if it's worth it or not. So you could, depending on where you are on that pendulum, you can say it's a disadvantage or an advantage. We have large memories, really fast CPUs, many core-based CPUs, lots of bandwidth. I think, especially when the outer header is only a 20-byte IPv4 header, I think it's a small cost to pay for all the benefits. How big do you anticipate the mapping cache getting in bytes for a network of the order of millions of EIDs? Well, we're designing Lisp to work for an IoT system. So we think having the mapping system store 1 billion entries is not much of a problem. You have to engineer and deploy the mapping system so it can handle the load of lookups from 1 billion places, looking up whatever they want. We don't think there's going to be n squared, where n is 1 billion type of connections, because that's just not feasible and not useful for scale. So we're going to see that the peer-to-peer network will help that a little bit as well. But now you can just select which RLOCs you use in those peers. You can decide, okay, if Paul is a peer-to-peer node with me at the Nexus level and he wants to open up a TCP connection to me to send transactions, he now can decide, I want to send packets to Dino through AT&T versus Verizon. Or I know Dino is connected to the same space satellite as I am, so I'm going to go that route versus something else. Previously, he couldn't do that. By having this level of indirection, he can do that. And he can always find me. Say I'm moving around and I'm changing my connections from AT&T Verizon to a Wi-Fi network and a satellite network. He keeps his connections up. So we don't have to resync it all just because our connection has gone down, right? Our transactions will stay in sync because he'll always be able to connect to my EID. The EIDs don't change as you move around. The RLOCs do. Just like the example with Anastasia. I talk to Anastasia all the time. She moves around all the time. I still talk to the same EID.
Yeah, just to carry on from that. So my question was really, how big is the mapping cache? If that mapping cache is going to be replicated in each of the XTRs in the Decent infrastructure, then using your analogy, everybody's going to have a copy of the phone book. How big is that phone book going to be?
Well, you're probably going to have a copy of who you want to talk to. So it's going to be probably a small fraction of the phone book, right? It's going to be, you're going to want to send transactions where the speed of light is reduced as much as possible. In other words, you're not affected by the speed of light latency. So your peers are going to be in your region of the world. And so those are the EIDs you're going to talk to, okay? Now, fanning it out more, then the seed nodes that are in Australia will talk to the seed nodes in Phoenix, for instance. But those are going to be a lot fewer so there'll be aggregatability at various parts of the world, just to make scale work, not only at the network layer, but also at the application layer as well.
Okay, thank you.
Are you afraid of obstructions from monopolies and competitors? So do you mean, will competitors do the same sort of thing, same sort of technology? Could you, GMI, could you rephrase what you mean? I want to make sure I'm talking at the right level. If you're talking about will monopolies take over the mapping system, we always have that risk that decentralized visions always turn into centralized implementations. And we've seen that with the miner pools in Bitcoin. That's always going to happen. And, you know, it's the same argument. Do I trust myself keeping my net worth on my own wallet, or do I trust somebody else doing it because they're paying insurance? It's going to be that same sort of trade-off, I think. Now, if the question was, If the question was, do we think there's competitors to Lisp? There's this huge market called SD-WAN, and it uses overlays. And there's a couple dozen companies that have been VC funded in the Valley and on the East Coast to build these SD-WAN solutions. And they're taking off quite a bit, but they all have their own solution. They all use IPsec at the network layer, but they all use their own control plane, so they really don't interoperate. In the spirit of openness and standardization, Lisp is the best choice because it's open and anybody can add to it, extend it, read about it. Nothing is patented. There's companies that have patented use cases for Lisp, but they can't patent the protocol because we built it in the IETF. And of course, there's open source implementations and closed source implementation, huge vendor support for it. So I hope I answered that question. So another question from Paul: how does an XTR know which other map servers XTRs to initially register when they want to join the network? Yeah, great question. It sounds like it's a bootstrapping problem. So you'll have to, what you do is you have to have a couple nodes that you first bootstrap to and then join the multicast group. And then once everybody joins the multicast group, then they'll all know about that multicast group. So those, what we do in the spec is we call it a peer group, and a peer group is a couple nodes that actually tell everybody who's in the multicast group so everybody knows about each other. We will not have to do that with the pull-based mechanism, because we'll take the EID and we'll hash it, and we'll say that node number 3, in other words, we hashed it to modulus the number of nodes, and node number 3 is responsible for this EID. And what we'll do is we map that into a DNS name, and then that will tell us the RLOC of the map server. So you see, we have different mechanisms and trade-offs that we could play around with for this. Yes, they would have to know the multicast group address that they're intending to join. How do you ensure EID uniqueness within the system? The same way you do on the capital I internet. You have service providers that have allocations, and you make sure they don't clash. What we're going to do with Nexus on the IPv4 space, we're going to use Class E addresses. Class E addresses start with 240, and we have the low order 3 bytes to use for uniqueness. And we're just going to use a random number for that. And if they're in the same instance ID or VPN, then they're unlikely to clash. 2 to the 24th is a small number, so there could be address collisions. But since we think not everybody's going to talk to anybody, we think the probability is way low. Having said that, we probably want to go to crypto EIDs because we get so many features. And now that random number is a hash of a public key, which is 120 bits. So if you go look up all the algorithms, 128 bits will duplicate in 100 years if you change it every 1 second. So none of us will be around to see the duplicate. So I'm not worried about it. Yes, I recorded it. We have a paid version, so you'll hear the whole thing. Let's say Google bans any Lisp apps on Android. They could, so could Apple. We can run Lisp as part of the application. We've thought of this problem once before. It turns out that Lisp can run in user space, so we don't even need to modify the Android kernel, even though we have a public domain implementation that does. And we do have a public domain open source implementation on Apple iOS that runs in user space as well. If they ban it, we will find other ways of using things, right? We will run at the application layer, and we don't go through Google networks. That's the only way I can approach it. But I don't think we're going to have this problem because we have working systems that already work. Maybe you say that because it's in test mode or it's small scale, but once it becomes successful, what's going to happen? Will the Googles of the world adopt it because it's successful, or come with an alternative with the same ideas because they want their approach to work? I've seen that happen so many times before. So I don't know. I would love to have that problem. Okay, any other questions or reactions? Did you like the format of this? I know it was a little bit fast, but maybe the subject was advanced. I'm not sure. Victor is on the call as well, and he's from Cisco and has been working on Lisp for quite a number of years. So if you have any questions about Cisco and Lisp, he might be able to answer them. And Victor's presentation from the conference should be available relatively soon. Go ahead, Mike. Can't hear you, Mike. Are you muted or you don't want to talk anymore? Oh, sorry, just pressing buttons. Okay. Well, thanks for raising your hand. Any other questions or reactions? Colin apologizes for not being here. He wanted to be here. But maybe we'll have a talk at some point about the proof of work denial of service attack protection. It's a really cool idea. Okay, so you guys have the slides. And if you have any questions, you could shoot them in Slack. We do have a Lisp channel. I don't know if it's public or private, but we in the marketing team could decide where to have that. So if you want to continue the discussion, what the appropriate channel is. Was it too technical? Was it the right level? Does it need more introductory information? That's good feedback. If you don't have to say it now, if later would be fine. Go ahead, Mike. Would Lisp require any limits on data sizes being broadcasted? No, but the application, we already found problems with sending large blocks on Nexus. We have to have Nexus lower the MTU, the maximum transmission unit, so there's enough room to put an extra Lisp header on it. So we have that already fixed and working. We found that right away, and by lowering the MTU on the interface solved the problem. Would Lisp require any? Okay, that was already said. Okay. Anything else? Okay, well, thanks for listening. I hope it was useful. And like I said, any comments, please send them to Slack. Thanks for attending, folks.
Thanks very much, Dino. Much appreciated.
You're welcome. See you later.